All right, let's do some mechanics. So, again, how this workbook is going to operate is most of the sections are applicable to both AP1 and APC mechanics. Anything specific, I will just take out the one it doesn't apply to. That's usually just the calc applications that go to mechanics. Although AP1 has fluids, so generally most of these are combined. So we're going to start just by defining vectors. So many physical quantities that we'll deal with in physics are vectors, and we can think of a vector as just a quantity that should be represented with an arrow, meaning direction matters. Now, everything we deal with in this class is going to have some sort of a size, which we call magnitude, but not everything makes sense to define a direction for. So, anytime we see vector, we should think of it as an arrow. And to describe a vector arrow, we'll describe it based on its components, which says how far left right the vector is versus how far up and down. And just so we're all on the same page, when describing vectors, we've agreed to define these quantities called unit vectors that just represent one unit of magnitude in a certain direction. Now, to avoid confusion with the coordinate systems, it's usually not the case that they're just labeled X, Y, and Z hat. We actually use I, J, and K. So I hat represents a rightward unit, J hat represents an upward unit, and this might be new. K hat actually represents a unit out of the page. So if we think about our sort of coordinate system, usually we do it like this, where positive x runs this way, positive y runs this way, and that's all I can represent on the paper itself. So if I had a third vector, it would have to come at me, which is what we define as positive z. You can think of it as like somebody shooting an arrow. So you see the tip of the arrow, which is why we get positive z looking like this. Versus k hat, negative k hat, that's just the sort of feathers of the arrow. And we'll talk about that a lot later. We're just going to be doing mostly I's and J's. So when we calculate the magnitude of a vector, we're really just looking at how long it is. And since we split our components, being x and y, all the triangles we can form are right triangles, which gives us access to the Pythagorean theorem. So that's going to be the first thing we try to prove, is that the formula for the magnitude of a vector is given by this expression, where it's the square root of the sum of the squares. Now, this really is just a restatement of the Pythagorean theorem, so we're going to assume that's true. We're not actually proving the Pythagorean theorem here. But basically, our usual setup for this is that we have some sort of a vector, and we would really like to know how long it is, which we denote with the absolute value bars. Because if you think about it, the absolute value really just says how long is that arrow in one dimension. So it's not really a reused symbol, it's actually the same thing. So if we have this sort of vector, we will always choose to break it up into its components. So it will be a certain distance left, right, a certain distance up, down. And by definition, this is going to be a right angle. So we can just do a squared plus b squared equals c squared. So one leg squared plus another leg squared equals the long side squared. And we can see that we square root both sides, and we do get the expected magnitude expression. So we will do a lot of Pythagorean triples here. I really like making all the numbers work out nice, and especially when we're dealing with square roots and right triangles, you try to use those Pythagorean triples when necessary. So you can expect a lot of 3, 4, 5s in your future. So the first actual physics quantity we will define is the displacement. And if we think about that word in English, displace, well, it means you're going somewhere or it's being removed. I always think of it as like the fluids. thing where you put a solid in a beaker and it displaces some water. It moves water from its original position. So the displacement just represents a vector that points from where you started to where you ended up. And this is a vector, meaning it has direction, displacement cancels. A lot of times displacement will be zero if you go somewhere and then come back. You've really displaced no net distance. But we still like to keep track of the total distance you've gone. And that's just d, the total distance. That never cancels. So it's a pretty straightforward illustration of what we have going on here, right? The distance, you're actually this is your step counter, whereas displacement, that's just your net results. So displacement sort of hides all of the in-between stuff happening. All right, an object travels 3 meters in the plus x direction, then 4 meters in the plus y direction. So we'll start off strong with kind of our first general physics principle is if you don't have a picture, you should always draw one. So we have an object that first traveled 3 meters, the plus x direction. Then we travel 4 meters in the plus y direction. And first, we want to calculate the total distance traveled by the object. So this is the step counter. Well, I went 3 meters, then 4 meters. So distance is just a scalar, meaning it is a number just with magnitude. There's no sort of direction attached. It's literally your step counter. It doesn't tell you where you've gone, it just says how many steps you've taken. That's why we say distance is a scalar. Now we want to determine the object's displacement vector in unit vector notation. So what that means is how far did I displace in either direction? So my displacement, well, we look at our diagram here. We see that we went 3 meters in the positive x direction, so that gets the unit vector I hat, because I have 3 copies of rightward length. And then I have 4 meters in the j hat direction. I have 4 units, the plus y. So let's draw a arrow that represents this. Well, always on these diagrams, we don't want to clutter them. Usually we're asked to draw a single arrow for each thing we want. So we have 3 meters and 4. So 1, 2, 3, 1, 2, 3, 4. I realize I do have an arrow tool, but I think I'm just going to freehand this one. And you should never mark these up, so I am going to erase this. You can see component-wise, does actually end up working out. So what is the magnitude of the displacement vector? Well, we are just asking how long is the slant right here. So this is our classic. This is going to become our sort of home triangle. Because whenever we're dealing with the Pythagorean theorem or square roots, you're almost guaranteed to just get an answer that's not going to be a nice rational number. So we can just directly use the formula. I encourage you to not set up the Pythagorean theorem every time. I encourage you to just get in the habit of just directly applying the magnitude result. When I say this out loud, I say it as the square root of the sum of the squares. Now, if you actually do this, you'll see 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, square root of 25 is 5. And all vector quantities have the same units as its component. So this displacement vector magnitude is 5 meters. So we will use this triangle and its siblings many times. So suppose instead we have this displacement, which is 4 meters I hat, and then minus 3 meters j hat. So negative in physics is almost always a direction indicator if it's a vector. Now, scalars, it can talk about like a going up or going down sort of thing. But for vectors, anytime you see a negative sign, that's telling you some direction info. So all this means is we're looking for 3 units in the negative j hat direction or down. So this is just 4 units right, 3 units down, which gets here. We can definitely draw better. So now we actually want to compare the magnitude of these two vectors. Now, it says to justify your answer that explicitly calculating this new quantity, which means that there must be some way to tell without actually plugging into the formula. And if you notice, it should be kind of suspicious that it is 3 and 4 again. So the key thing to look at here is that I know that when I do the formula, I'm going to end up doing Pythagorean theorem with 3 and 4 again. So I should get the same result. So in a lot of words, that's really what's going on here. So essentially, you have a 3 meter component and a 4 meter component. Doesn't matter how those are oriented because it's creating the same legs of the triangle regardless. So we can say the magnitudes have to be equal. And actually, as a consequence, that actually means these vectors are just rotated copies of each other. And since magnitude is a distance, this actually means both of these vectors sort of live on this sort of circle of radius 5. These vectors are rotated copies of. This is the question about displacement and distance. So if there's a question to know, it is this one. This is a pretty basic example, but it does come up quite a lot. So we have a car traveling counterclockwise around a track. You want to rank the total distance the car has traveled upon reaching A, B, and C, and the displacement vector magnitude of the car upon reaching A, B, and C. Well, distance is the step counter. So if the car just starts tracking, well, the odometer is probably a better word for it for the car. So if you just start keeping track of your distance, the car is obviously going to keep gaining distance, gaining distance, gaining distance, gaining distance. Right? Distance can't cancel. Distance is a scalar. So step counter is just strictly increasing. So we can say that it has traveled the least distance at A, then it's traveled a bit more distance when it's gotten to B, and then it's traveled more distance. So this is really just as simple as saying distance is a scalar, so distances can't cancel, and it's always strictly increasing. Now, what about displacement? So displacement, that's really the length of the vector from the car's starting position, which is this 3 o'clock, to A, B, or C. So notice that if we start drawing some vectors here, this would be the car's displacement, A. This would be the car's displacement to B. And this would be the car's displacement to C. So what we can gain from this diagram is that notice that there's zero displacement at the start because the car has not moved yet. Then the car is getting farther away, farther away, farther away, farther away, farther away. B is the farthest away the car is ever going to be. And then it's actually going opposite the way it came. So its displacement begins to shrink. So due to the canceling, we see that A and C have the same displacement magnitude. The arrows are different direction, and B is the greatest. So this is, of course, due to the fact that displacement is a vector. So we're really just asking how far away from the starting point is the car at A, B, and C. Well, it's a little bit far away at A, It's its maximum distance away at B, and then by symmetry, A and C are the same because they're on opposite sides of the clock. So instead of giving components, it's usually a pretty common thing to be given the angle. So you could be given two pieces of info. I have the X and I have the Y, and then I can determine other things. But sometimes you'll be given polar form, which is I tell you how long it is, and I tell you what angle it's directed at. So notice that's still two pieces of info regardless. It's just a different piece of info. Now, we're usually most comfortable giving this angle with the horizontal. So again, we define this angle as with the horizontal, because if I draw a dashed horizontal line, it's the arc that the vector makes with that horizontal. Well, we could just as well be given the angle with the. So to figure out this relationship between components and angles, we do have to use trigonometry. And yes, we could go through the whole process of SOHCAHTOA for all the trig functions. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. I like to think of these trig functions as tools. Cosine is the adjacent leg extractor. If you would like the leg that touches the angle, so touching means see how the arc actually touches the leg. If you want the leg that touches, stick a cosine theta to your expression. If you want the leg that does not touch, tack on a sine theta. Now, for finding angles, you actually do want to use the SOHCAHTOA with tangent usually. But this is such a common thing we do in this class. This is just worth sort of committing to memory. That if you ever want the leg that touches an angle, just tack on cosine theta to the hypotenuse. If you ever want the side that doesn't touch the angle, tack on sine theta. And you can prove this or see where it comes from because notice this cosine theta is associated with the adjacent leg, just like in our SOHCAHTOA definition. Get the same thing as. So this works regardless of what the angle is. So if instead you're given like this angle phi, you could say that this side would be v cosine phi, and this side would be v sine phi. It's all about whether the leg is touching or not touching the angle. That determines what trig function is. So that's why it's best not to memorize that, like, oh, horizontal is always cosine, vertical is always sine. Not necessarily. It depends on what's defined. Now, I am a big user of the horizontal, so 99% of the time it's going to be this relationship, but sometimes we get some funky angles. So this is how we break down a vector from polar form to component form. Now, this doesn't actually give you the sign. You have to just look at the picture and tack on pluses or minuses as needed. So we got two vectors. One is components form, one is polar. So first we want to get the left, right, up, down of V1. So anytime we have a angled vector, it is almost always the case that we're going to want to break it. So first of all, notice that this part of V1 points left. So this leg points left. So I actually need a negative when I use my components here because left is negative in the x direction. And then there's also a upward piece here. So this would be positive. All right, so now to determine in component form, we just know that each of these legs, we'll move this a bit out of the way. We know it's going to be sine and cosine. So first of all, notice that my hypotenuse is 13 and my angle is 23 degrees. This 23 degrees touches the horizontal side, so I can say that this side will be 13, tack on cosine 23. Yes, you will get this if you do the whole SOHCAHTOA definition, but it saves you so much time if you just recognize that if the angle touches, use cosine. If the angle doesn't touch, use sine. Now, if that component is cosine, this one will always be sine. They're always paired that way, right? That's why it's sine and cosine. And now we can actually compute what that is. So if you use Desmos, just make sure Desmos is in degrees. But I, of course, have my lovely TI-84 from when I was in high school. And I'm sure I picked these that they round somewhat nicely. You'll start to kind of know what the good angles are that make things work out. So if I do this, 13 cos 23 is roughly 12. 13 sine 23 is roughly 5.1. So V1 in component form is the horizontal component is 12, but it's left, so negative 12. And then the vertical component is 5.1 meters, but that's positive. So this is our vector in component form. So we really didn't do anything except express the vector in a different language. This represents the same thing as the angled picture. But notice it's a lot easier to sort of plot. What is the magnitude of V2? Well, V2 is already set up for us that it's in component form. So the magnitude of V2 is just going to be Pythagorean theorem. So we take the square root of the sum of the squares. And since it's addition, the order that you put the things in the formula doesn't matter, right? Pythagorean theorem doesn't care what's A and what's B. This is exactly 1. Work that out. All right, now calculate the angle V2 makes below the x-axis. So we're actually interested in this angle right here, which we will call theta. So for angle finding, it usually is helpful to use the full SOHCAHTOA definition. So notice this 0.8 touches, so I would call this adjacent. And this 0.6 does not touch, so I would call this opposite. Which means I should probably use tangent. Although you have all three sides, so if you trust your calculation, you could do any of them. So I could say tan theta is equal to the opposites over the adjacent. Also, don't use sines when finding angles, right? Triangles have actual positive lengths. The negatives are just to help you get the orientation. So if we do that, we get, what is that, 3 over 4. So we get tan theta equals 0.75. So to actually solve this, we have to undo the tangent function. So to do that, remember that anytime you do anything in algebra, we're talking about inverse operations. Well, we just literally have a function whose job it is to undo tangent. So we undo tangent on both sides. And we get theta is equal to inverse tangent of 0.75. And if we do that, making sure we're in degree mode, this is also known as arctan. Sometimes you'll see it like this, or you could type it in like this as arctan of 0.75, but this is probably what, 20, oh, 37 degrees, we'll say. This is a very common angle you'll see that makes nice. All right, last thing we'll do, just with straight vectors, is addition. So addition of vectors works exactly how you'd expect it to in terms of algebra, where if you're adding vectors, we just sort of do an add like terms thing, where the x components add and the y components add. Now, geometrically, we think of vector addition as sort of like a displacement journey where we just do all the vectors as like a sequence of instructions and see how far away we ended up. So what this means, it's called tip to tail addition, where maybe this is my first vector, this is my second vector. Well, the vector sum would just be sort of the displacement on all your segments. So you're sort of just thinking of it as like a sequence of steps. This will be more clear from context. Now, we don't actually have to define subtraction differently because subtraction is just addition of the opposite. So you can think of vector subtraction as just subtracting like terms. Geometrically, it involves sort of reflecting the vectors when you do the sequence of steps, but I can't really imagine that coming up. We have a special name for the vector sum. It's called the resultant, like result. But here's just another description, it's just showing you that tip to tail. I do V, then I do W. That's where I ended up. So pretty straightforward how we define it. Now, the issue is in context, since we can only really nicely add vectors when they're in component form, it usually involves just breaking it down using the trig functions until everybody is in terms of i's and j's. All right, so now we'll do a just typical addition example. So we have vectors that are in unit vector form, and we want to calculate their sum first in component form. So in component form, we have just this idea of combining like terms. So we have 2i plus j is one of our vectors, negative 5i plus 3j. Another. So we can just think of this as combining like terms. So I have positive 2 and negative 5, which makes negative 3 units I hat. And then I have 3 and 1, which makes 4. Huh, look at that. I wonder what we're going to have to do with this sum. Oddly suspicious. You're gonna see I overuse these numbers. Not sorry about it. All right, now we're going to draw the addition geometrically of these and verify it doesn't really matter what order we do them. So v plus w, v is 2i plus j. So I go 2, then 1. That would be doing v. And then w would be 5 left and 3 up. So then I go from v. I go from v's endpoint. I go 5 left. So 1, 2, 3, 4, 5. And then up. Up 3. That sends me here. And therefore, the sum is just the line connect. And if we check it, we see that there's 1, 2, 3 units in this direction. And there's 1, 2, 3, 4 units in this direction. So as expected, it is a negative 3i plus 4j. Now, order doesn't matter. I see that I did not make a big enough grid. Don't know how I didn't notice that when I edited, but whatever. We can also do w plus v, meaning I could do the 5 left, 3 up first. So let's actually do my best here. Make my own grid from scratch. See, I did not make a mistake. The grid was always big enough. So if I do W first, that would be 1, 2, 3, 4, 5. 1, 2, 3. So this is W. Then I can do V, which from that position, it says I go 2 right, 1 up. 2 right, 1 up. Wow, look at that. We're exactly where we thought we'd be. Which is 3, 4. So -3 units in the x direction and 4 units. So I will make sure to fix this figure time. All right, what's the magnitude? Wow, whatever could it be? Also, realize direction is all the negatives say, so just do not put negatives in your square root when you do the Pythagorean theorem. You will mess it up somehow. So we said that v plus w was equal to -3 I hat plus 4 j hat, which as a picture is this. So of course the magnitude of v plus w is just the square root of the sum of the squares, and wow, it's 5. Common mistake, well, I don't know how common it is. It's not 7. You can't like you can't do this. You can't like distribute the magnitude. That doesn't work. So just be wary of that. All right, last one. We got some breaking down to do. So we're eventually tasked with determining each of these vectors in component form, calculating their displacement, graphing the displacement, magnituding the displacement, directioning the displacement. But to do any of that, we got to break everybody down into components. So let's kind of speed run this. So for the angled ones, we see that R1 is up and right. So both of these can be positive. 23 touches the adjacent side here. So this is positive 13 cos 23. This is positive 13 sine 23. Then this vector is left and up. So this would be negative 25 cosine 16. Should be putting degree symbols everywhere, but we don't really use radians. And then this would be positive 25 cosine, or so, regular sine. And R3 is easy because it's just vertical. So this is really just -3 j hat. No splitting involved. So now we gotta do some number crunching. We got 13 cos 23 and 13 sine 23. Oh, I remember that previous problem. So breaking down delta R1 is roughly positive 12 meters in the I hat direction and positive 5.1. I don't know if we need the double pause. 5.1 meters in the j hat direction. Then delta R2, breaking that one down. We have to remember to put in the negative for there. So 25 cosine 16 is really close to 24, but it is negative because that is a leftward vector. Negative 24 meters. I hat plus, it is plus because it's going up. 25 sine 16, which is 6.9 meters j hat. And then delta R3, well, that's just 3 meters down. So there's 0 I hats. And then there's -3 meters in the j hat. So let's work this out. Calculate the net displacement of the object in component form. Well, we just need to add these together. So we'll see if I can do this in my head. I know I wrote this so the numbers work out. Sure, I did it to do something nice. Let's see what happens. Well, 12 and negative 24, because again, we're just adding like terms. So we should think about this as like splitting the columns. So adding the I-hats, I have positive 12 and negative 24, and 0 makes negative 12. And then in the J's, I have 5.1 and 6.9, which are positive. That makes above my page 12. And then I subtract off 3, like 9. And I know I'm doing something right. Sick of it yet? The cousin of our 345 friend. Draw the object's net displacement using the component form of the resultant. So, of course, we don't actually have 12 grid lines here. I did that intentionally to make you recognize that this is a scaled copy of our friend. So, because again, 12. 12 is the same thing as 4 times 3, and 9 is the same as 3 times 3. So this is like a scaled up 3, 4, 5 by factor. So what does this look like? Well, this would look like this, right? Because there's 1, 2, 3, 4 units that way and 3 units. What is the magnitude of the object's displacement? Also, whenever we add a bunch of things, we usually call that the net result. So the magnitude of the net displacement, that's just going to be what? 12 squared plus 9 squared, which makes 15. And now we can calculate, it says the angle it makes above the negative x-axis. So whenever you're asked to calculate an angle, please actually draw in the triangle. So this is the angle we want, theta. This we said was 12 meters. This we said was 9 meters. So once again, we can use tan theta is opposite for adjacent, which is 0.75 again. So we actually get that same answer as before. Theta equals arctan of 0.75, which is roughly 30. And I know that because this is the 345 angle. So it shows up a lot. So not a lot of physics going on right now, but a lot of just plug and chug away math and lots of 3, 4, 5 triangles.